Hey viewers, this is Devinder Kaur and welcome to my YouTube channel, The Enlightened Room. In this video, we're going to study about the trends in modern periodic table. So before studying the trends in modern periodic table, we all should be very well known about the atomic properties. Now what these atomic properties are? Those properties which show a regular gradation or variation on moving from top to bottom within the same group or from left to right along a period are known as atomic properties. Now to understand these atomic properties, watch this video complete. In the atomic properties, we usually take up valency, atomic size, metallic or non-metallic character and chemical reactivity. So now let us discuss briefly about the trends in these properties one by one. Now number one, let's talk about the valency. We all know that valency is defined as the combining capacity of an element. It depends upon the number of valence electrons, that is, the number of electrons present in the outermost shell of the atom. Now, how does the valency vary in a period? On moving from left to right in a period, the number of valence electrons increases from 1 to 10. Now, as you can see clearly from this table, it is clear that sodium has 1, magnesium has 2, aluminium has 3 valence electrons. Therefore, these elements can easily lose their electrons to acquire the stable electronic configuration to the nearest noble gas, that is neon. Therefore, the valency of sodium is 1, that of magnesium is 2 and that of aluminium is 3. Now, silicon has 4 electrons in the valence shell. Now, it means that it can either achieve the stable electronic configuration to the nearest noble gas either by losing, gaining or sharing its 4 electrons. Since large amount of energy is needed to either lose or gain 4 electrons, therefore, it prefers to achieve the stable electronic configuration of the nearest noble gas argon by sharing the 4 electrons. So, it can be said that silicon has a valency of 4. Similarly, phosphorus, sulfur and chlorine have 5, 6 and 7 electrons in their respective valence shells and thus need 3, 2 and 1 more electron respectively to acquire the stable electronic configuration, or you can say stable electronic configuration to the nearest noble gas, and that is argon. Therefore, the valency of phosphorus is 3, that of sulfur is 2 and that of chlorine is 1. Now the last element, argon, has 8 electrons in the valence shell or its octet is already complete. Therefore, it does not have any tendency to form bonds. Thus, the valency of argon is 0. So, what we have concluded that on moving from left to right in the period, the valency of elements first decreases from 1 to 4 and then decreases to 0, and this happens in third period. So, it can be said that in a period, the valency of an element is either equal to the number of electrons in the valence shell or 8 minus the number of electrons in the valence shell. Now, let's talk about the variation of valency in a group. Now, all the elements in a group have similar electronic configuration. That means they have same number of valence electrons. Therefore, the valency of all elements in a group is fixed, or you can say it is same. You can take the example of this group number 1. Now in group 1, that is in the group of alkali metals, they have 1 electron in their respective valence shell. So the valency of all elements of group 1 is 1. Similarly, all the elements of group 17, that is halogens, have 7 electrons in their respective valence shell and thus need 1 more electron to complete their respective octets. Thus, the valency of all the elements of group 17 is also 0. So, moving on to similar lines, we can show that valency of all the elements of group 2 is 2, those of group 13 is 3, those of group 14 is 4, those of group 15 is 3, and those of group 16 is 2. And also it should be noted that valency of all the elements of group 18, that is of noble gases, is 0. Now why? Because these elements have their respective octets complete except helium as its duplet is complete and hence do not enter any chemical bonding. Now let's talk about the atomic size. Now if an atom is considered to be a sphere, the atomic size is given by the radius of the sphere and is commonly known as atomic radius. It can be defined as the distance between the center of the nucleus and the outermost shell which contains electrons in an isolated atom. Atomic size is usually expressed either in angstroms or in picometers. Now let's study the variation of atomic size in a period. On moving from left to right in a period, the atomic radius decreases. Now as you can see, as we move from left to right in a period, the atomic number of each succeeding element increases by 1. This means the number of protons in the nucleus and the number of electrons in the extranuclear part increases by 1. The addition of this extra electron takes place in the same shell, but the addition of extra proton to the nucleus increases the nuclear charge by 1 in each succeeding element. Now due to this, what happens? The increased nuclear charge, or you can say due to this increased nuclear charge, the electrons are attracted closer to the nucleus and hence the atomic size decreases. Now you can take the example of atomic size decreases regularly from lithium to fluorine in the second period and now from sodium to chlorine in the third period. Now one more thing to be noted that in any period the noble gases has the largest size. You can see the example of second period, there is neon that has the largest size, while in the third period the argon has the largest size in that period. Now the reason behind this is that in case of noble gases the atomic radius refers to the van der Waals radius, while in case of all other elements the atomic radius refers to the covalent radius. And by definition, van der Waals radius of any element is larger than its covalent radius. Now let's talk about the variation of atomic radii in a group. On moving down a group, the atomic radii of elements increase gradually. Now as you can see through this table, as we move down a group, a new shell of electrons is added to each succeeding element. For example, lithium has 2 shells of electrons K and L. Sodium has 3 shells of electrons K, L and M. Potassium has 4 shells of electrons K, L, M and N and so on. As we move down a group, the number of shells increases. As a result, the distance between the nucleus and the last shell increases and thus the atomic size increases from top to bottom. Also, as we move down a group, the atomic number increases and hence the nuclear charge, that means number of protons in the nucleus, also increases. As a result, the force of attraction of nucleus for the electrons increases and the atomic size should decrease. But the decrease in size due to increased nuclear charge is much less than the increase in size due to addition of an extra shell of electrons. Thus, the increase in atomic size as we move down a group from lithium to francium is primarily due to addition of an extra shell of electrons. So it can be said that atomic size increases down the group in spite of increase in nuclear charge. So this was up for today's video. In the next video, we're going to study more trends of the modern periodic table, in which we will discuss about metallic and non-metallic reactor and chemical reactivity. For more videos like this, subscribe to my channel and click on the bell icon. Thank you so much.